Okay, good morning, everybody. It is my pleasure to introduce Per Salberger, and he will speak on counting rational points on cubic hypersurfaces.
Okay, thank you very much for the invitation. Let me first say that if I'm less energetic than usual, it's because of fever, but I hope I will still be able to give a decent talk. So, as usual, after at least in this millennium, I like to count points. And for that, I will need a height function, and I will do it over Q, and it will be the usual one. So if you have an n+1 tuple, then I will just take the, so if this is then a primitive n+1 tuple, I will just send it to, I will just take the maximal one. So this is, I will use that to quantify. And the aim of this talk is then to give a kind of a survey talk of counting problem for cubic hypersurfaces, and especially then in low dimension. And I'm inspired by dimension growth conjecture by Heath, Brown, and Serre, and also by the Manin conjectures. And I would like to combine them in a certain way. So this is what I'm inspired of. So then for a subvarieties then, defined then over Q, then I will let then here VQ of B will then be the set of points at height at most B. And I'm then interested in the asymptotic behavior, interested then in asymptotic behavior of this function VQ of B when B goes to infinity. And I mean, if you are interested in the Manin conjecture, so then you may look upon historically, why was Manin interested, why did he formulate this conjecture? This was because he was interested in non-singular cubic surfaces. So he had written a book about that, and then he saw some features, and I think this is still the most famous fun variety. So I would like to start with that just to illustrate the problem. So if then X now P of 3 is then a non-singular cubic surface, over Q, then you have of course that this is then grows like a B square if X contains a Q line. So the interesting is rather what happens outside the lines. So if you then look at the complement, and you take then the unions of all the lines, then Manin then, he conjectured then that you should have an asymptotic behavior like this. You should have that UQ of B should grow like a constant times B log B rank P, rank of the Picard group of X minus 1. And then here C is then a kind of a Tamagawa number here. And then there is a conjecture what C should be. This was not by Manin, it was by Per. And so this is the conjecture. But of course here, if you want C to be positive, you have to assume that there is a rational point. And then there are many, now, the truth is actually that this is not known for a single non-singular cubic surface. So in spite of it, what motivated this conjecture, so this illustrates how hard these conjectures are. So, but it's even worse than that. It's not known for a single non-singular cubic surface with xq non-empty that this uq of b have linear growths. So then you can react to several ways. You can say that let's do some other problem or some simpler problem, but you can still also try to obtain the best possible result for non-singular cubic surfaces. You can try to find the best possible upper bounds. And in that respect, I would let me point out that it was not even known that you have quadratic rows until 2002. So then Brown found a bound which was better than b square. And the best bound then up to date for a single non-singular cubic surface is the following result by Brown. And it's still now 20 years old, so I think it's really time to find something better. So if now x is now a non-singular cubic surface with the three coplanar Q lines, then he proved that this UK of B is bounded by B4 third plus epsilon. And to do that, he used then the fact that each line gives rise to, you can look at residual conics, so you get three conic bundle structures, and then for each point he uses to say the most favorable ones. So, but this is still a rather small class of cubic rational, non-singular cubic surfaces, and for most, for the majority, you can't do as good. So what you have in general is the following result. So if x is a non-singular cubic surface, then you have the following. You have that this best upper bound. And I proved this, I think it's almost 10 years ago now. It was published maybe 4 or 5 years ago. So it's 12 over 7 plus epsilon in general. And further you have that, you have also that if you have one line, then you can combine this with a conic bundle technique. I mean, combine this proof, then you can do better. So if X contains a Q line, and you can do, if you have two Q lines, you can do even better. You can do then, no, sorry, this should be 8 over 5. So if you have two lines, you can do then if X 3/2, if X contains two Q lines. And finally, if you have three, which don't have to be coplanar, then I can do 18 over 13. So I think these are the best known bounds up to date. And it would really be very interesting if someone could beat those bounds. I mean, if you can find a non-singular cubic surface with a prove that it has slow growth, and or if you could beat this general bound. So one can always try to look for inspiration for function field case, and then you have more tools, because if you use just hyperplane section argument, then you get elliptic curves, and you know more about elliptic curves over function fields. So for function fields, you can actually prove this bound here for non-singular, for all non-singular cubic surfaces by combining arguments by Hirsch, Brown, and Mester if you just transform them into function field case. So, but I don't, even in function field case, I don't know of any better bound than this. I don't know single non-singular ones, cubic surface where you have can prove it, you have a slower growth. So there is a discrepancy between conjectures and results. You can also consider then to try to find better lower bounds. And of course here, if you have a conic, then you have immediate linear growth. But I don't know any other techniques to prove linear growth for cubic surfaces. So if you have, for instance, if the Picard group is C, I don't know how you can prove linear growth. I mean, and that's, so it's not only that we don't have good upper bounds in general, we don't even have good lower bounds for non-singular cubic surfaces. So the situation is not fantastic. So then, if you can't, I should say, in the function field case, you can obtain good lower bounds by deformation theory. Because if it's defined, for instance, over the finite field, then you get the problem instead where you look at rational points on a surface defined over finite fields, and then you can use Grothendieck's theory of Hom schemes and deformation theory. And then there is a well-known lower bound using you have Hom and X groups of the cotangent sheaf. You find it in Collard's book, and then you can actually prove that you have linear growth. I mean, you can get a low bound, which does not depend on this argument with conics. So it's slightly better in the function field case.
Does it also give the logs?
What? Logs? No, I'm not looked into that. So maybe you can do that. But I mean, no one is really. You don't get much credit if you prove something over function fields. So I think you can probably do, but I have not done it. Now if you can't solve a problem, then you look at a slightly easier problem. So then the next one would then, so many people have looked at singular, oh, oops, this is not at all. See, So many people have looked at singular cubic surfaces. I mean, there's a classification, I think, by Derenthal. You look at singularities. If you have normal cubic surfaces, you have rational double points, and there are some 15 classes or so. And for most of them, there are now asymptotic formulas. The reason it's simpler to deal with singular cubic surfaces is that I mean, I invented a method in the 90s. So you look at universal torsos, and so instead of counting rational points on the surface, you count integral points on universal torsos. And some of those varieties have simpler universal torsos than others. So non-singular cubic surface has terrible universal torsos. I mean, have a lot. You don't have any good embeddings and nice equations. I mean, not when you want to count. So you have to realize here it's not just a question of geometry. So I mean, for a cubic surface, you can parameterize sometimes. It could be Q-rational. You can parameterize all points, but that doesn't mean that it's easy to count. So you need to have nice equations, I mean, in order to count. So it's not enough if you have a good birational description. It's very much has to do with, you need precise equations, which you can use. So, but some singular cubic surfaces have very simple universal torsos, and some have maybe not so simple, but they're still easier to deal with than for non-singular cubic surfaces. So let me then first state the conjecture then here. So if X a normal non-conical, of course, cubic surface, over Q, then you have the following conjecture. It's the same, you remove the line, so you have that this maybe now you don't have 27 lines, or you don't if it's a singular, but you still have a asymptotic formula of the same shape, log B rank of the Picard group. But now it's not this X anymore, so you need it then for the minimal resolution. Then, so for then a crepant resolution. There is one canonical minimal. You have rational double points, and it's well known you have a natural resolution. So this is what distinguishes, say, singular Farner varieties in dimension 2. I mean, you have one canonical resolution with very good property, which does not change the canonical class. So here you have to look at the rank of the Picard group of the resolution. And then this is now known in many cases. And I think there are many people here, like de la Bretèche, Browning, Le Boudec, so there are others. So the simplest case is the first case was due to Batyrev-Manin. And then they looked at this x0 square cube equal to x1, x2, x3. And in this case, you have just the 3A2 singularities, and you have then here 3 lines. And they interpreted this was just a special case of their work on toric varieties when they used this method from Tate thesis with the abstract harmonic analysis to prove asymptotic formulas. And then I noticed that you can also approach this in another way. I gave another proof with universal torsos, and then in my approach, and then I use these universal torsos by Collier-Telaine and Saint-Sucre for counting problems. And then instead then I look at the model then here. So let me still write like that. So I lift them to the universal torsos, and then I count points on universal torso. I should say I think around the same time Per had some similar ideas. But before that, no one really used torsos. And after that, there were people like de la Bretèche, and then they refined analytical tools. So when you count points here, you can use techniques from lattice point counting and so on. There was then a tremendous activity here. So let me just quote 2 results here, which I found particularly amusing. I like extremes, so I take the cases where you have very few lines. So you have first one result by Derenthal and Joyce, and then you have then the following equation. Then here x1 x2 square plus x2 x0 square plus x3 cube equal to 0, and here you have just one line. And you have then an E6 singularity. They proved an asymptotic formula on that. So this means that they're asymptotically equivalent. And then there was another result by Derenthal and Bayer. I think they did it independent. I mean, this I think is a common paper. Oh, I should have written it in the other order, but anyway. x1 cube plus x2 x3 square plus x0 x1 x2. And what's interesting with this is that it has just 2 lines, and that you have then one A5 and you have one A1 singularity. So these 2 cases are interesting from another point of view, that they are compactifications of a principle of a homogeneous space under an algebraic group. So they are both compactifications of homogeneous spaces, under then here GA cross GM here. But they are not principal homogeneous spaces. So in the case where you have principal homogeneous spaces, then there are Tanimoto and Chinkel, they have used that to prove asymptotic formulas. So it would be interesting to see if you can use this structure to give alternative proofs, because that is not used. I should say, by the way, that this observation here is, I think, due to Derenthal-Lauren, so that they are compactifications homogeneous spaces. So that would be interesting if one could extend these techniques from abstract harmonic analysis. So I think that's all I wanted to say about...
Arbitrary coefficients?
Sorry?
Can you put arbitrary coefficients?
All the three?
1, 1, 1, and that's always, this one else.
I'm sorry, I don't...
The methods which are used there.
The method.
If you put coefficients to the web as well? Or?
No, I mean, they use... they look at the universal torsos and they have just one equation, but I mean, I think this is maybe 50, 60 methods. I mean, each surface is its own word of slightly different techniques. So maybe they have been proven 10, 12 such examples, but I think they're all slightly different. So I'm not able to tell you about the technique. So it's very different from the techniques. It's still different from the techniques by the Chinkel gang with abstract harmonic analysis. So yeah. So now still those cases here have nice universal torsos in the sense that there's a machinery with Cox rings. You can produce equations for universal torsos. And if you have here you have no equation. I mean, here it's very simple. It's just an open subset of A9. But of course you have to count lattice points in a nasty hyperbolic region. But it's still much easier than this case here. But still here you have only one equation. But if you get, as soon as you get two equations, it gets much harder. So the following result is not an asymptotic formula, but it's still impressive. So for then this Cayley surface, so if you look at this surface, 1 over x2 plus 1 over x3 equal to 0, then Heath-Brown proved the following, that you have then b log b over 6 is then bounded from below by nub or uqb, and you have an upper and lower bound. So that would be maybe a major breakthrough if someone can prove an asymptotic formula for that, because that would be the first example where you have a slightly more sophisticated universal torso with two rings for the Cox equation. So now I would like to go discuss some other cases here. You can also deal with non-normal cubic surfaces, and that is actually, I think, much easier. There was a paper, de la Bretéche and Browning and myself, so let me just reproduce the result. So it illustrates that it's a bit different. So here we have a non-normal cubic surface. So this surface is famous in differential geometry. It's a Cayley ruled surface. It's not so famous in arithmetic, but you can still consider it. So it's de la Bretéche, Browning, myself. I don't have the time to write that. So if then here x is defined by the following equation, x0, x1, x2, minus then x0 square, x3, minus x1, 3 equal to 0, then you have then here the following, and now you have to look at the, you have to look at the whole surface. So then you have then here that x q of b is an uq of b is, now let's see, you have a ruled surface. Yeah, you have an asymptotic formula for everything. So you have a whole family of lines, and each of them contribute with b squared. But you can still prove an asymptotic formula here, and it looks like this. We have O b3 half log b. So here you cannot really use this conjectures of. By the way, this refinement to singular ones here, I think it was in paper by Pierre. It was also by Chinkel and Batyrev how to refine these Manin conjectures in the singular case. Here you really have to, you cannot use Manin conjectures, but there are conjectures by Batyrev and Chinkel very general conjectures, and this result is compatible with those conjectures, and we also compute this constant, I mean, and prove that it's correct. So I should also say that here there are other results. There's a mathematician I don't know. He's called Mayansky. There is a preprint on Archives 1 year ago or so, where he looked at some other non-normal cubic threefolds, I think. The paper, it was not, I mean, there are some details lacking, but he treated many cases, each in 10 lines or 5 lines or so. But anyway, it was a bit sketchy, but this is a paper I know about on the non-normal cubic surfaces, hypersurfaces. Let me just say that it's not very interesting to consider them because there are very few of them. As soon as you go to dimension at least 4, they are all just cones. So to say the non-normal cubic surfaces are only interesting in dimension 2 and 3. So let me just write that down, because in the sequel I will tend to concentrate on normal cubic hypersurfaces, and there are good reasons for that. So let me just then make this remark that any non-normal cubic hypersurface of dimension bigger than 3 is just a cone. I mean, so it's only interesting to consider, I mean, dimension 2 and 3, and in this paper by Mayansky, he dealt with some cases in dimension 3. So now then I would like to then discuss, I mean, in what happens in higher dimensions, in dimension 3 and 4 in particular, and then I would like to refer then to the, I'm inspired then by the dimension growth conjecture. And this is due to independently by Serre. You find it in his book on lectures on model Weil groups, and for instance, and topics in Galois theory, and it was also due to Heath-Brown. Maybe Heath-Brown was first, but I mean he only formulated it for hypersurface, and Serre formulated it in much generality. Anyway, they did it independently. So if X is then an integral subvariety. I mean, of course, you can do this for number fields or global fields. I just formulated here. If this is an integral subvariety of degree d at least 2, then this conjecture says that this x QB should have a growth like the dimension of x plus epsilon for any epsilon. And here you have to be a bit precise. There is one uniform version and one non-uniform version. So Serre's version I think is like that. But in fact, in many cases where you can prove it, you can prove that this implicit constant here will only depend on the degree of x and the surrounding dimension of Pn, and it will not depend on the specific equations. But let's put it like that, because So the main aim of my talk is to now to relate this conjecture to how you can improve this conjecture starting with the Manin conjectures. You can get a more down. You can improve this exponent if you just remove, say, linear subspaces and so on. So normally these are different words. I mean, this Manin conjectures they are more studied for non-singular varieties of those which are close to non-singular, while these conjecture by dimension growth conjecture are more for very singular varieties that they are interesting. But I mean, for in the cubic case, those words are not so too different from each other. Because I would like to tell you now that if you have a normal cubic hypersurface, then you actually have canonical singularities, and then this gives you a much more down-to-earth consequences from these Manin conjectures, which are close related to this dimension growth conjecture. So let me first then tell you what's known about that. So even if you're just interested in cubic surfaces, cubic hypersurfaces, you sometimes have to know estimates for other auxiliary varieties. So let me then state it in general what's known, although I will only really be interested today in cubic hypersurfaces. So this dimension growth conjecture, so we have then a theorem then. First then there was a paper in Duke by Browning and he's Brown and myself. And then it says that this DGC, it holds if D is at least 6, and then I prove that this holds in general. So this holds in general. I hope, yes. So of course, if it's false for linear varieties, I mean, so the point is that if you look at the hypersurface, you have always a trivial bound, the dimension plus 1. I mean, if you have one equation, you can always eliminate, so to say, one variable. So the point is, if you have a degree higher than 1, then this is really a non-trivial bound. And the hardest case is actually the cubic hypersurfaces, and I used an ad hoc technique. So if you exclude the case of cubic hypersurface, then I can actually prove a uniform bound. But it's still open for cubic hypersurface if you can do it uniformly. So this will just be a kind of background. So let me then just say what this means for a cubic hypersurface. So for a cubic hypersurface, then if I have then here, if I then have x contained then in Pn, then we do then have that then this gross x of q of b will then be gross like O b. It will then be b n plus 2, and then it will be then minus let's see, no, then it will be b. Yeah, it will then be b. I have dimension n, so it will be n minus 1 plus epsilon here then. So for instance, if you have a cubic surface, you will get then b square, and that was not known even before 2000. So so this is the general bound you have for cubic hypersurface if you apply this dimension growth conjecture. So what I would like to discuss today now is how you can do something, how you can improve upon this. But then of course you have to remove linear subspace, because if you have then here a linear subspace of codimension 1, then you already hit this bound. So this is then best possible. So if now here x contains an n minus 2 plane over Q, then you have already we have then growth, which is then at least already then be n minus 1 here. So this cannot be improved. So you have to remove those. And now. But in general, of course, for a generic one, you expect in general n plus 1 minus d. So for a generic cubic hypersurface, then we expect then that it should grow like b. We have n plus 1 per parameters, and then we should expect then minus 3, because we have a choice between B3 values. So, and this is, of course, by the circle method and so on, you can show that for non-singular ones. So the point here is now that I would, for the cubic hypersurfaces, generic case is not so far from the general case because you don't have so much difference. So in fact, what I would like to do is to prove this for non-normal ones. I want to go down from dimension growth conjecture and go down one dimension here to n minus 2. But then, of course, I have to remove the linear subspaces. And I would like now to see what you can deduce from the Manin conjectures in that aspect. Because now I only as I said, I only really have to deal with normal cubic hypersurfaces because the other ones are not can be dealt with separately. And then I made an observation 1 year ago or so that they actually you always have canonical singularities if you take a non-singular, if you take a normal cubic hypersurface which is non-conical. So if then say x is then p of n and n is at least 3, if that is a non-conical, oops. If that is a non-conical normal, a cubic hypersurface, then X has at worst canonical singularities. So it's important here that n is at least 3 as well to do the reduction here. So what does it mean? So one definition is then that there exists then a resolution here, pi from x tilde to x with then pi star omega x tilde equal to omega x. I should say that this is of course false. I mean, if you go to quartic or so, hypersurface, it's not true anymore. But this is a nice feature that unifies, I mean, all those normal cubic hypersurfaces. So let me just then sketch a proof of this. So in case you have a normal cubic surface, then there have been there's a lot rich literature. For instance, you have the seminar called Polytechnique, led by De Massure. You find in spring lecture notes. So this is well known if the dimension of x is equal to 2. So the idea is now to use a hyperplane section argument to deduce it in general. So, and then I will also use, I think, results. It's convenient to use results by L-Kick, I think, that since these are Gorenstein, then it's the same that to prove that it has rational singularities. So it has rational and canonical singularities are the same thing for Gorenstein. In the Gorenstein case, we have Gorenstein here in hypersurface. So if then dimension x is at least 3, then we use a Batyrev-Manin argument. So let us then choose a point here. So I mean, I work over an algebraic closure, of course. So let then here x p then belongs to x. I take a point, and then and let then here x1 be the blow up at p, and then say x tilde to x1 be a resolution of x1. Now we have then here a map. So we have them here the projection map. So we have then here a projection morphism, morphism here from x1. So you project from this point P. You can't define it on x, but when you blow up, you get a morphism to Pn minus 1. And then what we do is now that we just use the Batyrev-Manin now we just use then the Bertini for, say, in Kleinman's version you find in Hartson's book, then for this x tilde to Pn minus 1. And this will now gives you, we will use that to find a case such that the inverse image of a hypersurface here will also be non-singular. It will also be, yeah, will also be non-singular. So let's see here. And then I can use induction oops. Oh, that was too. Yeah. Let's see that one. Poop. Yeah. So now you can just use induction. So I use this Bertini to, I just finish my phrase here, to find hyperplane H containing Pn with then a P containing H such that this inverse image then here, such that the inverse image of x tilde to this Pn of let's see here, of x intersected with H is non-singular. Is non-singular. And now you can just use induction to prove. So if I call this pi, to prove that Ri pi lower star of Ox tilde is equal to 0 at P. So this if I is positive. So this stochastic does not depend on the choice of resolution. So you can use different resolutions for different points. So, but whatever you do, you can prove that at each point you can find a resolution such that this is vanishes, and so this gives you then this result for all cubic hypersurfaces. So this means now that we can formulate nice consequences of the Manin conjectures for which are closer to in style to those dimension growth conjecture. And because this alpha invariant now will, or Fujita invariant, I think it should be called, is now at most n minus 2. So this gives some hope to improve upon this dimension growth conjecture, at least conjecturally. So let me just point out here, so remark here, if then x of p of n is non-conical and normal cubic hypersurface and pi x tilde x a resolution, then we do have that this canonical class here, k of x tilde, is now equal to the pullback of the canonical class of x, plus and the sum of all those exceptional divisors, which are now have then here positive coefficients in here. So if now, so for then, if you take then here the hyperplane divisor or the corresponding sheaf here, then we get then here from this that this this Fujita invariant, which occurs in the Manin conjectures, this is now the infimum of all A in R, such that this is or maybe C of such that this C of L plus this class K x tilde belongs to the effective cone. This means that this now is bounded by the degree of minus k of x, and this means this is equal then to the dimension of x minus 1 here. So in case the degree of x is equal, by the junction formula here, if the degree of x is equal to 3. So I will then have this, this Fourier invariant is then bounded by n minus 2 for normal cubic hypersurfaces. So let me then just briefly formulate these Manin conjectures. So as you know, there was an original version where you removed some accumulating subsets, and then you expected that on the open complement you should have an asymptotic formula on Manin's type, but then there was a counterexample by Batyrev-Manin. But then some years later, I think it was Manuper observed that those could be explained by that those points come, you have additional points coming from covers. So you should not only remove subsets, you should also remove contribution from certain covers, and you should remove thin subsets. So I don't have the time now to formulate that conjecture. Let me just write down the explicit expected asymptotic formula, and I can refer to, there was a very good survey article by Lehmann and Tanimoto, for instance, you can find on archive about this, where it's formulated precisely. So Manin conjecture now, Manin conjecture then here predicts that we have an asymptotic, that we have a growth, like constant times b, a, this Fourier invariant x of L, and then we have then here some log of some other invariant b, which I don't have the time to define and which will not play a role in this talk, and then we have minus 1. For then suitable subsets, for a suitable subset then here of x, q, and b. And in the first version, you just removed some accumulating subsets, and in the later versions today, which have not yet been contradicted, you have to remove some thin subsets. So if you now start with this conjecture, and if you use this result that the Fourier invariant is at most n minus 2, then you can deduce the following result. We deduce then the following conjecture from this Manin conjecture. Conjecture. So let me then write down a very concrete conjecture here for cubic hypersurfaces. So now you can actually prove that some of those potential accumulating subsets are not dangerous, because if you have, say, of degree 2 or more such subsets, then you can use the dimension growth conjecture for those subsets in order, so to say, to improve the dimension growth conjecture for the big variety. And if you use then my result there, and I also have result of the dimension growth conjecture, there's also one in Serre's book for covers, which I can't prove for double covers, but for other covers I can prove that. So then I deduce the following result. The following conjecture is a consequence of the previous conjecture then. So if now here x is, if x here, x of Pn of q is normal non-conical cubic hypersurface with only finitely many, n minus 2 planes, and then the following holds then for the complement, holds then for the complement. So I mean, I remove all those linear planes. So we should then have that this uq of b should grow like, we have this Fujita exponent here, bn minus 2 plus epsilon. And now if you're skeptical and if you believe that the Manin conjecture should be wrong also when it comes to this constant, I still think that it has not been contradicted, the original, I'm not sure, conjectures when it comes to the constant. I think there's a log factor. But if you mistrust, if you believe now in the modern version with the thin subset, then I also have, it could be potential that I have plus contribution here from double covers. For the triple covers and so on, I can prove that they are inside here from finitely many double covers. I mean. So this is a conjecture I can deduce from the Manin conjectures using, I mean, this observation here. So now I should say also that I will just come to this example by Schmidt and Rudelier 5 times. In that case, you can actually then you actually get then here that these have this gross order. So there are double covers where it can occur, but usually I think those double covers should be very special. I don't know an example where this gross order should be higher than that. So I expect that this should also be able to absorb that, but I don't know how to prove that, how to deduce that from Manin's conjecture here. Okay. So now I would have liked to present some result for oops, no, that one. In dimension 3 and 4, let me just say that this is not known for a single non-singular. This is not known here for a. This is not known for a single. I mean, if I now cancel that, it's not known for a single non-singular cubic hypersurface of dimension 2, 3, 4, 5, 6. So if you, for instance, if you take one of the best results is that if you look at this, one, x0 3 plus x1 3 plus x2 3 minus x3 3 minus x4 3 minus x5 3 equal to 0, then we have by this classical result by Vous b 7/2 plus epsilon. So, and this has not been improved, and I don't know any fourfold. Let's see, 6, 8, maybe like that, yeah. So I don't know any fourfold where you can do better than that. So we are still a bit away from that. So, but one can look at singular ones, and then for singular ones, some of them resemble singular cubic surfaces. So there is one example by de la Bretèche where he looked at the Segre threefold. I mean, it's a very impressive paper. I think it's 70 pages or so, where he proved an asymptotic formula. So he proved the Manin conjecture. So it's a cubic threefold. We have 10 singular points. It's a maximal one you can have. And then there are some results for singular cubic fourfolds. And one result is then due to Blumer, Brüden, and myself. And then we dealt with this equation: x1, y1, x0, y2, c plus x2, y2 equal to so. So then has then an asymptotic formula. Then confirming Manin conjectures. Confirming then Manin conjectures. Manin's conjecture. So I gave a talk about that in Pisa about this. It's a scenery cubic form. I mean, in 6 variables, and you get a fourfold. And then I said, this is the only one I know about apart from toric one. But then Martin Widmer was there. And then, but look, there is another one by Schmidt. And then I never heard about that paper by Schmidt. And then I looked at Matzeinet. There were only 2 quotations. So that was completely unknown. But then I looked, I mean, the other week, now there are 40 quotations. So although this paper was published a long time ago, it has suddenly become very, very famous. And it inspired then a thesis by a student of Chamberlois, I think, Le Rudelier, which then gave a counterexample to the original, I mean, Manin conjecture. It also told you that you have to modify, I mean, the original expectations of these conjecture pair constant a little bit. So let me then, don't know, oh, my time is already out. Okay, my plan has completely failed. So I've completely failed. So I don't know how to do it. Maybe I will just then end with that, and then I don't have the time to tell you about my own work related to that. So we have the following example. We have then here a cubic x, which is then equal to the symmetric product of P2. So I will stop in 5 minutes, so don't worry. Maybe even before. This is then of Wolfgang Schmidt. And then you have that this is then defined by a so I like to write it like this. And then I have then here x1, x2, x1, x2. And then we have then here x3, x3. And this should then be, so this is then a hypersurface in P5. And now this turns out that this is the equation of the symmetric one, because there is a natural morphism here from P2 cross P2 cross to this hypersurface, where you just have coordinates here y tilde y and z, which then goes to those x, where you then have that x2i then are equal to y I zi, and then you have then xj plus k equal to 1/2 ij zk plus yk zj. And one way to see this is that from this you get this could be the symmetric matrix corresponding to quadratic form. A quadratic form then in 6 variables, and then you just factorize that into linear forms, and then these are the corresponding. I mean, this tells you then that this form is reducible, and this is then the factorization, and this gives you then this morphism. And now here, what he did, Schmidt, was that he proved an asymptotic formula here. So then we have then here a diagonal here, so let then here u then be equal to x minus n delta, which is then here the diagonal. Then we have then two sources here of oops. What is this? It's that one. Sorry. So we have then here 2 cases. So we have then here we have them here a natural double covering here. So we have then here uq of b And then we have those points which comes to the image of P2 cross P2. And then we have those UQ of B, which do not come from the image here. And in both cases, Schmidt proved that this is equal to a constant here times B square log B. And then we have then here B square log B. And now it's then exciting then to compare this with the Manin pair conjectures for this, because you have a natural resolution here. It's well known that you can look at the Hilbert scheme. You have a natural resolution, and then Le Redullier, she computed this pairs constant, and then she found out that this actually corresponded to that case. So now what I was interested in, and which I have not time to talk about, I should say I'm not finished yet, is that I look at the Hankel determinant. So I look at the hyperplane section where x2 is equal to x2 tilde. And then I get a threefold instead. And this threefold is interesting because it occurs, for instance, in the work by Bagava, where he looks at the average rank of elliptic curves. So he looks at binary quartic forms of a certain type. So there are two invariants for those, and this is one of the invariants. So this is related to binary quartic forms, and it has many. If you take this hyperplane section here, you take x2 equal to x2 tilde. So then what I am working on right now is to try to prove that you have the same phenomena for these threefolds, because I don't know of any other example on lower. There have been some other examples of the same kind, but I don't know any one of dimension 3. But then it's much harder, because the strategy of Schmidt was to, here when you have rational points here, two things can happen. You can either come from rational points, like if you come from the diagonal, or you can have two conjugated quadratic points. And then he made a kind of descent, although it was not a ramified cover, so you had to deal with separately each quadratic number field, and then he made a summation. But in my case, then, it's not enough to just count points here on P2 of a quadratic number field. I will get an equation here, bilinear equation here, so I have to use the circle method then here for each contribution here. So I have made some heuristic calculations for the main term, and it seems to confirm that I get exactly the same phenomena as in this case. So I have not yet dealt with the error term, so. But I mean, I think that would be an interesting example, because this Hankel threefold, as I said, it occurs, for instance, in the work by Bagava and his collaborators. So I have to stop here. Sorry for the.
Thank you very much for this obviously not failed overview. Are there any questions? Well, I had a question. In your growth conjecture, what was it called? Dimension growth conjecture, you said you could do something uniform for degree at least 4.
Yes.
Uniform as in what?
Yeah,
uniform how? What do you mean by uniform?
So I will lecture about this so-called determinant method. So it was started with Bombier-Pila, but then Hirschbaum developed it to periodic method. So a feature of that is that if you have a bound for a variety, then this implicit constant does not depend on the equations. It depends only on the degree and on epsilon and the surrounding projective space. So because you get a different implicit constant for each variety in general, but not here. So
not even on the size of the coefficients?
No. So this is the point. This is why you can do induction, you see. Because if the constant dependent on the variety, then you could not work by induction. So the reason that Pila, he proved a general bound for all varieties was that he had a uniform bound for affine curves. And then from that, he deduced a bound for all affine varieties, since he could start with something uniformly. So usually you prove something uniform in low dimension. And actually the strategy of this dimension growth conjecture is that you reduce to a hard problem for affine surfaces. And then you just use, so you destroy the homogeneity. So you look at the affine cone, and then you just use hyperplane sections. So it's very important that it is uniform to. So the argument for dimension 4 or more is very different from the argument in degree 3. So then it's not uniform. It's an ad hoc argument. So, yeah.
Thank you. Any other questions? Wait.
Can you maybe say a bit more about the circle method part in the end?
Sorry?
Can you say a bit more about the circle method part in the end?
Second.
The circle method part.
The circle method. Well, actually, I've consulted an expert because I think he could do it much faster than me. So the point is that I look at this equation x2 equal to x2 tilde here, and then when I translate that, I plug this in because I use exactly the same strategy as Schmidt. So I don't count point here. I count point on the double cover. And then when I have then a quadratic point, then I get points defined over a quadratic extension here. But I view them as with a kind of Weil restriction as rational point on a form in 6 variables. Because you have a conjugation, so you can find new coordinates where these are defined over Q. So it's like a trace, you see, you have norms and traces and so on. So it will gives you, in each case you will get then here a bilinear, so to say. You get a bilinear equation. And that's defined over Q, and the idea is to apply the circle method instead of just counting the P2. So I'm not convinced yet that the error term, the estimates of the error terms will be sufficiently good because then you have to sum over all. I should say also that this threefold is fascinating. I mean, if you look at the minimal resolution, it's related to the famous Schwarzenberger bundle of P2. I mean, if there's a vector bundle of P2 by Schwarzenberger, and this is exactly the minimal resolution. It's a P1 bundle associated to this Schwarzenberger bundle. So it's exciting for a geometer in this example. So, but there is probably hard work for in analytic number series. So I don't know if I will succeed. So, yeah.
Other questions? Then thank you very much again.
Oh, thank you.